In this lesson, I'm going to talk about homomorphisms, or in the context of vector spaces, they're known as linear transformations. A homomorphism is similar to an isomorphism, except some of the conditions are removed, and we'll see that on the first slide where we define the concept and then give some examples. So, for example, when two vector spaces are of different dimensions, it's not possible to define a bijection between them. For example, if you have R3 and R2, in such cases, it's possible to define what is called a homomorphism. A homomorphism requires only the linearity property, and we've seen that several times before, so I've written it out here. In some cases, you'll see this as two separate things, where you have just the removing the scalar and then just having the sum of two vectors, and then yet there's another way of stating that's equivalent, where you just have f of v plus bu and it equals this, and you can show that these two are equivalent. But I'm going to go with this definition here. In the context of vector spaces, as I mentioned, this is homomorphisms are often referred to as linear transformations. There's some other terms that are also used. Linear map or linear mapping, you'll see that sometimes. Let's look at our first example. We have the function f from R3, three-dimensional Euclidean space, to R2, and it's defined as follows. F of x, y, z is mapped to x plus y, with the second component being y plus c. And we want to show that f is a homomorphism, so we need to show the linearity property. We take two vectors from R3 and then take the linear combination of those two vectors, so a and b are scalars. Then we use the definition of addition for R3 to add these together, and we get this here. And then we can do the mapping as defined. So we add this and this together to get the first component, and this together to get the second component. Then we just do some internal rearrangement to get to this line here. Then to get from this line to this line, we're just using the property from R2 of, or the definition from R2 of addition. So if you add these two together, you come back to this. And then we use the property of scalar multiplication in R2 to go from here to here. We've just factored out the a and the b. And then this first term equals a times f of x, y, z. And the second term equals b times f of x prime, y prime, z prime. So that proves that we have a linearity property, which means that f is a homomorphism. As I mentioned, we've used the definition of vector addition and scalar multiplication from R2 and R3 in some of these steps here. Let's see what else. So the function f maps R3 to all of R2. So f is surjective. To see that, you just take anything in R2, z1 sub z2, and if you take f of this vector here, then you add z1 plus 0 and you get this, and 0 plus z2 and you get this. So for everything in R2, there's something in R3 that maps to it. The problem that it's not an isomorphism is the injective part, the one-to-one part. So for example, we have f of 1, 2, 1 equals 3, 3. But we also have f of 2, 1, 2 equals 3, 3. So the function f minus is not a function, and thus f is not an isomorphism. So we don't have one-to-one here. We have two things getting mapped, actually an infinite number of things getting mapped to the same vector in R2. It's enough to just show that you have one counterexample, which I've done here. We have a couple more examples. In the first example, we map from R to R2, so it's from smaller to larger. That's also possible. Here's our function, f of x equals 2, 2x. So every real number gets mapped to this pair here. And then to show linearity, we take f of x plus by, where x and y are from R, and a and b are scalars, but they happen to also be from R in this case. Then we just use the definition of the function to get this. Then use the definition of addition in R2 to break this into two pieces. And then use the definition of scalar multiplication in R2 to factor out an a here and a b in the second term. And then we get af of x plus bf of y, and that proves linearity. Then even simpler is if you have any two vector spaces v and w, you can define the zero homomorphism. It's just every vector in v gets mapped to the zero vector in w. Homomorphism maps the zero vector to the zero vector. We mentioned that before. That's the same proof that we used in Theorem 26, so I won't repeat that here. Theorem 26 applied to isomorphisms, but the proof doesn't involve anything more than what we need for a homomorphism. This fact may be helpful in identifying when a function is not a homomorphism. So in some cases, you can just look at the definition. Like I give an example here. You have f of x, y, z equals x plus 2, y plus z. But if you put in 0, 0, 0 here, you get 2, 0, which is not the zero vector. So without even doing any more checking, we know that this is not a homomorphism. A homomorphism f from v to w is determined by the mapping of its basis for v. So that's similar to what we had for isomorphisms. Then we have a definition here. Let v and w be vector spaces and S be a basis for v. The function f mapping S to w is said to be extended linearly to a function f prime v to w if for every v and a little v, an element of our vector space v, f prime of v equals this linear combination here, where v is represented as this linear combination of S. And just one cautionary note, I should have probably been more careful. I used f prime here. I don't mean the derivative of f. I know that's a common notation. This is just the extended linear function. I could have used f sub 1 or something else. Theorem number 32, we have a basis for a vector space V and a set T, a multiset actually, T, I'll explain what that is in a second, of elements from another vector space W. If we have that, then there exists a unique homomorphism from V to W that maps Si to Ti for I equals 1 to n. So a multiset is a collection of elements with the possibility of repeated elements, whereas a regular set, you're not allowed to have repeated elements. So this gives us a little bit more flexibility. We can have, for example, we could have S, the elements of S mapped to the zero vector. So we would have 0 n times in here, or there's other possibilities. I'll give you a few examples after I do the proof. So the proof starts like this. We let G be a function that maps from S to W such that G of S sub I equals T sub I for I equals 1 to n. So that's the part of the requirements for our theorem. Then we linearly extend G to a function from V to W such that for every V, is written as a linear combination of the vectors in S, f of v equals this expression here. So you just take the coefficients and then you multiply them times the elements in t, which, as I say, may be repeated. So this function is well defined since each v is uniquely represented in terms of the vectors in S. But what we haven't shown yet is that f is a homomorphism. And we'll do that on the next slide. So let's finish off the proof. We need to show linearity of our function f, and we also need to show that f is unique. That was part of the theorem. So to show linearity, we take v and u in our vector space v, and we write both of them as a linear combination of the basis vectors. And then we take f of av plus bu. We plug in v and u, as I've done here. Then we collect the coefficients based on the different basis vectors. You see here, so this is just the reconfiguration of this line. Then going from this line to this line, we make use of the definition of our function f. So we have this output, and then we collect all the terms that have an a and an a sub I, and all the terms of the b and the b sub i's together. And then this first term is a times f evaluated at v, and the second term is b times f evaluated at u, and then we have our linearity property. In terms of uniqueness, assume there's another homomorphism h such that h evaluated at s sub I equals t sub I equals 1 to n. Then take any v, write that as a linear combination of the vectors in our basis s. Then we have h of v equals this expression because h is a homomorphism and we have the linearity property. But then we've defined h of s sub I to equal t sub I, so we can go from this to this. But then we have the same definition for the t sub i's for f, so we go from here to here. And of course this is f evaluated at v, and so now we've shown that h equals f for every possible value in v. In other words, they're equal. So why do we use a multiset in the previous theorem? I gave you one example when I started. Let's look at a couple more. So let v equal R2 was the standard basis, E1, E2, and let W, the other vector space in our theorem, equal just the real numbers. Then we can define T to be the multiset 1, 1, and the theorem guarantees a unique linear mapping from R2 to R such that f evaluated at E1 is 1, and f evaluated at E2 is 1. And that map is actually f of xy, an element from R2, equals x plus y. So if you put in either one of our elements, just to test this out here, if we put in E1 here, then you would have a 1, 0, right? That's what E1 is. And then you'd get 1 plus 0, and that would give you 1. And if you have E2, that would just be 0, 1, and you plug that in here and you get 0 plus 1, which again is 1. So it fulfills the mapping. If the theorem was restricted to regular sets, in other words, not multi-sets, we would exclude a valid mapping, which we've just shown here, unnecessarily. So the theorem gives us more flexibility. We have another example, maybe that gives a little bit more motivation. Here we have v, our vector v is R5, and our vector w is R3. And we want to we define our function f, and we have the standard basis, I should say first, for R5 and R3. So we take t to be E1, E2, E3, the standard basis for R3, and then we just, anything else that can't be represented here, we map to the 0 vector. And in this case, we map the first 3 elements of the standard basis from R5 to the standard basis R3, and we map E4 and E5 to the 0 vector in R3. And the mapping that fulfills this is f of x1, x2, x3, all the way up to x5 equals this expression here. So for example, if you took E1, that would be 1, 0, 0, 0, 0, 0. Then you'd have 1 times E1, so that would give the mapping we want. Same thing for E2 and E3, but if you had anything that was only a linear combination of E4 and E5, in other words, where the x1, x2, and x3 were 0, then you would map that to the 0 vector. Okay, so some motivation for why we use the multiset, and let's continue. I have several more theorems on this topic. We need a result that I'm going to leave as an exercise to the listener. Let's have a look at that. So show that the set of functions capital F, V, comma, W form a vector from a vector space V to vector space W is a vector space in and of itself where addition and scalar multiplication are defined as follows. So if you take two elements from our set here, all the functions from V to F, we take two of them, then we define addition as being applying the function F sub 1 to V and plus the function F sub 2 of V. So that's the definition of adding two functions from this set. And then scalar multiplication is if we multiply a scalar times our function F and apply it to V, then it's defined to be the scalar times F evaluated at V. Okay, so as I say, that's an exercise for you to have a look at. You need to check the 10 axioms. A lot of it will follow from just either V or W being vector spaces and having the various properties that you would need to employ in order to prove that the capital F of V comma W is also a vector space. Then we have another theorem that's related. It's the set of all homomorphisms from a vector space V to W, denoted by script L VW. That's also a vector space. And that's our theorem 33. The addition and scalar multiplication for script L of VW is the same as we've defined for the capital F V comma W. And I'll also leave this as an exercise to prove, but I'll give you a hint here. It's a little bit easier. Once you have this proven, then we have basically the task of showing this L of V comma W is a subspace. So in order to do that, we can use theorem 2, which says that if a non-empty subset of a vector space is closed under addition, vector addition and scalar multiplication, then it's also a vector space. And so we only need to show that LVW is non-empty in order to make use of theorem 2. And that's true because we know the zero homomorphism is in the set. So we know it's not empty. And now the task is just showing closure for the elements of L, V, comma, W. And that's what I'll leave as an exercise. I have some additional notation on this slide here. I mentioned some of this before, but I didn't formally write it down. So let me do that here. For a function f from x to y, so x and y are just sets. They don't even need to be vector spaces. X is known as the domain, and y is known as the codomain. I think I've used that term codomain and domain before. What I haven't mentioned was the image of a function, and that could be a subset of y. It's basically everything that f maps to from x into y. As I show here, it could be a subset. It could be all of y, but it could be a subset. And that's called the image, or sometimes the range of x under f. And the dimension of the image space is known as the function's rank. Then we have a remark here. Omitting the onto requirement does not make an essential difference between isomorphisms and homomorphisms, since each homomorphism is onto some space, actually its image. So if you have a homomorphism from vector space x to vector space y now, and we can always say that f is onto f of x, the image of the mapping. The real problem in terms of differentiating between homomorphism and isomorphism is the one-to-one property. We can't fix that by just mapping to the image. And I gave an example previously, example 1, where we had a function and it mapped two different elements to the same element in the image 3, 3. So just wanted to make that point here. That'll come up actually even in the theorems that follow, come up in terms of the talking about an image as opposed to the codomain. So I just wanted to make that distinction clear here. We have two related theorems on this slide. Let's look at the first one. Under a homomorphism, the image of any non-empty subspace of the domain is a subspace of the codomain. So that's saying that homomorphisms map subspaces to subspaces. To do the proof, let F be our homomorphism and V and W be our vector spaces, so F maps V to W. Let S be a subspace of V. The image of S, F of S, is a subset of the codomain W. It could be all of W, but it's at least a subset, which is non-empty, since S is not empty. That was in the assumption of the theorem. And since S is not empty, we can make use of theorem 2, which we already used once in our previous theorem, to sort of have a shortcut in determining that S is a subspace. We just need to show that it's closed under linear combinations. So we take two elements from F of S and scalars A and B. We take the linear combination of these two elements. Then we can bring A into the argument and B into the argument because F is a homomorphism. And then we can combine these two arguments again because F is a homomorphism. This equals this. And then this is an element of F of S since AU plus BV is an S. And so in other words, this linear combination is an element of F of S, and that proves our theorem. We have the sort of the reverse of this. For a homomorphism F from V to W, V and W being vector spaces again, the inverse image of a subspace S in the range F of V is a subspace of the domain V. So it's a little bit hard to see, but I drew us a picture. So you have V and W, and F is a homomorphism between V and W. And then F of V is a subset of W. It could be all of it, but it's at least a subset of W. And we're told that S is a subspace contained in F of V, but a subspace of W. And the theorem is saying that the inverse mapping, the preimage of S, this thing here, F inverse of S, that this is a subspace. So given a subspace here in W, you have a subspace in the V. So it's sort of the opposite or the reverse of what we had here. And we'll use a similar way of proof. S is a subspace, so it contains the zero vector. And since F is a homomorphism, we have that F of the zero vector of V is mapped to the zero vector of W. And if we take the F inverse of both sides, we have that the zero vector in V is in F inverse S. So F inverse S is not empty. And then we can use theorem 2 to prove that it's a subspace. We just need to show that F inverse S is closed under linear combinations. So take two elements in F inverse S and two scalars. The fact that these are elements of F inverse S implies that F evaluated at U, F evaluated at V are elements of S. Then we have that F of AU plus BV equals A F evaluated at U plus B times F evaluated at V, since F is a homomorphism. And then this linear combination is in S because these two elements are in S, and S is a subspace, so the S is closed under linear combinations. And then we can just take the inverse of both sides, whatever this happens to equal in S, and that proves us that AU plus BV is an element of F inverse S, which proves our theorem. The null space or kernel of a homomorphism F, mapping from V to W, is the inverse mapping of the zero vector in W. In other words, it's everything that gets mapped into the zero vector. The dimension of the null space is known as the function's nullity. And in terms of notation, we write it this way here. So the null space of F is the inverse of the zero vector in W, or it's all vectors in V such that F of V equals the zero vector in W. So just returning to an example we had seen earlier, consider the function f from R3 to R2 defined by this mapping here. We previously proved this was a homomorphism. The elements of R3 that are mapped to 0, 0, in other words, the zero vector in R2, are elements in R3 such that x equals minus y and z equals minus y. We're just solving these two components equal to 0. And so we can write the null space of F as all vectors x, y, z, and then plugging in minus y for x and minus y for z. We have this here, and we can factor out the y. And so it's all multiples of the vector minus 1, 1, minus 1. And so this is of dimension 1. It's just a line in R2. And so the nullity of F is 1. All the vectors in the image of F can be written in the following form. We can just break this up into x0 plus yy plus z0z. And then we have, we can factor out the x, the y, and the z. And we see here we have 3 vectors. And the middle vector here, 1, 1, can be written in terms of the 1, 0, 0, 1. So it's of dimension 2. I give a little bit of different argument down here, but basically the image space is of dimension 2. And thus the rank of the image space of F is 2, as I said. Notice that the rank of the image space plus the nullity equals the dimension of the domain, which is 3. And as we'll see in the next theorem, that's always true. The dimension of the range plus the dimension of the null space always equals the dimension of the domain that you're mapping from. The sum of a homomorphism's rank and its nullity equals the dimension of its domain. So let F be a homomorphism from vector space V to vector space W. And just keeping in mind where these entities are, the nullity is the dimension of all the vectors in V that are mapped to the zero vector in W. And then the rank is the dimension of the image of V in W. And we want to show that the sum of those two equals the dimension of the domain, in other words, the dimension of V. So we start by letting S sub n script equal S sub 1, S sub 2 up to S sub k be a basis for the null space of F. In other words, assume the nullity is k. And assume the dimension of V is greater as n, which is greater than or equal to k. And then by theorem 16, which I've recopied down here for us. Any linear independent set S in a vector space V can be expanded to form a basis for V. So by this theorem, we can expand the basis for the null space to be a basis for all of V. And since we assumed V had dimension n, we just write it out like we have here. If we can show that T equals f of s k sub k plus 1 all the way up to f of s sub n is a basis for the image, then we're done. Okay, so we first show that T is, the set here is linearly independent. Let's take a linear combination of the vectors in T and assume they equal the zero vector in W. And since F is a homomorphism, this implies this here. We can use the linearity property. And so the argument, this expression here, is in the null space of F. And since S subscript n is a basis for the null space, there exist scalars a1 to ak such that we can write this element of the null space in terms of the basis of the null space. In other words, this expression here. And then we can just take all these terms on the right and move them, subtract them on both sides, and we get this expression here. However, the vectors in S sub V are linearly independent since S sub V is a basis for V. Thus, A sub I equals 0 for I equals 1, 2, 3 up to n, which implies that T is linearly independent. So let's continue on the next slide. So we want to also show that T spans the image of F, in other words, F of V. So we take any member of the image called F little v and represent V as a linear combination of the basis S sub V. So we have that here. We then have the following: F of V equals F of this expression. Then we use the linearity property of F, since it's a homomorphism, to write this like this here. And you notice I kind of broke it into the nullity part and then the part we added to it to make a basis for the entire vector space V. Since S sub I equals 1 to k are in the null space, then F of, by definition, right, F of S sub I equals 0 for I equals 1 to k. So these all drop out. They're all 0. So we get that F of V equals a linear combination of the these additional vectors, or the F mapping under F of these additional vectors. And that's an element of the span of T, which is what we wanted to prove. If you recall at the beginning of the proof, we said if we could prove that, then we're done. And thus, T spans the entire image of F. So if the nullity of F is K, then the dimension of the image of F, i.e. the rank of F, is n minus K, and their sum is the dimension of V. Okay, so that's the proof. And then I have an exercise for you. Prove that for a homomorphism, the image of a linearly dependent set is linearly dependent. The following theorem relates several concepts that we've been talking about. It has 5 parts, and they're all equivalent to each other. So we need to prove sort of a circular relationship amongst the different elements here. So let's have a look at it. For an n-dimensional vector space V and homomorphism F from vector space V to vector space W, the following statements are equivalent. The function f is 1 to 1. Keep in mind a homomorphism doesn't require this, so if this is an additional condition. So if this is true, then the function f has an inverse from its range, f of v, back to v, and the inverse is a homomorphism, and that in turn is equivalent to the kernel or null space equaling just the zero vector, and that is equivalent to the rank of S being n. We kind of know these two because of the previous theorem. And then if we have a basis for V, then the mapping of the basis under F is a basis for F of V. So the plan to prove this is we're going to show 1 and 2 are equivalent, and then we'll show that 1 implies 3, 3 implies 4, 4 implies 5, 5 implies 2, and then that'll give us, these two together will give us a loop linking all these together as being equivalent. So we start by assuming 1 is true. This implies the existence of F inverse, which maps from F of V back to V. Take a linear combination of elements from F of V, this here, and then we apply F inverse to this linear combination. And then we can use the linearity of F, since it's a homomorphism, to write this argument is in this form here. And then if you have the inverse of a function, it's just the argument. And then you can work backwards and write U is F inverse F evaluated at U, and same thing for V. And so you have this linearity property for F inverse. So in other words, F inverse has an inverse, and it's a homomorphism. So that implies this way. Then assume 2 is true. And in general, if a function has an inverse, then the inverse must be 1 to 1. So 1 holds true. That's generally true for functions. And I give you a reference here if you wanted to look further into that, the Wikipedia article on inverse function. Okay, so let's continue with this part of the proof on the next slide. Let's finish the proof. I copied the equivalent statements here so we can refer to them. So let's look at the first one here. 1 implies 3. F is 1 to 1 implies the null space is just a zero vector. And that holds true since all homomorphisms map the zero vector to the zero vector in the codomain, and a 1 to 1 map sends each member of the domain to one member of the codomain. Then 3 implies 4 holds true since by definition the rank plus the nullity equals the dimension of the domain. So we're given that the nullity is 0. In other words, so that would imply the rank would have to be n. And 4 implies 5. So if F is of rank n, and we have a basis for V, then the mapping of the basis into W is this set here is also a basis for F of V. So we only need to show that this set here spans V, since by 4 the dimension of V is n, and by theorem 18 in an n-dimensional vector space, a set of n vectors is linearly independent if and only if it spans. So if we show it's spanning, then we get linear independence, and that gives us that we have a basis. So take F of V, an element of the range, F of capital V, and write V in terms of the basis for V, vector space V, that which I've done here. Then we have F of V equals F of V written in terms of the basis, and then we use the fact that F is a homomorphism to write it out like this. And so we have for any F of V in the range, f of v can be written in terms of this set of vectors. So in other words, it spans, and then by 18, theorem 18, it's linear, these are linearly independent, and we've shown that the set is a basis. Okay, so finally we need to show that 5 implies 2. So assume 5 is true. Take u and v, small u and v, and vector space v such that u does not equal v. The two vectors have unique representations in terms of the basis v. That's an implication of a basis. So we have these two vectors written in terms of the basis, and since they're not equal, it means at least one of the pairs of coefficients is not equal. We'll just say aj does not equal bj. The assumption that this set here is a basis for f of v and aj doesn't equal bj implies that f evaluated at u equaling this set does not equal f evaluated at v being this set here, because of the inequality and the uniqueness of representing something in terms of a basis, which we assume from 5. So thus f is 1-to-1, because we've had u not equal to v implies f evaluated at u is not equal to f evaluated at v. Okay, so that completes the proof. I have another lesson following this on representations with regard to a homomorphism, and I'll present that next.